Okay, so good afternoon. I will speak about what we call event biasing, or which is also called the bias reduction. And Alberto has already mentioned several things about that. And we go in this presentation through the various options which exist in Gen 4. And I will insist in particular on what we call the generic biasing, which is meant to be a general scheme for biasing. So next slide. Okay, I don't see the slide. It's I'm still on the first page. Okay, thank you. So I will tell about what is biasing first in the introduction. Then I will go through the various options which are existing in Gen 4 since quite time. I will give a bit more details about one of the most advanced features of biasing in Gen 4, which is the reverse Monte Carlo. And which has this special feature that in this biasing technique, you have part of the simulation where the particles go back in time, so which is a quite special feature. And then I will explain this generic biasing scheme. So next slide. Next one. So there are simulation problems in which we are interested is rare. And so it can be rare because of the physics, or it can be rare because of the setup, geometrical setup, or in general, this is rare because of the two. So let me give you some examples of such problems. Assume you want to estimate the efficiency of a shield, that is, you're working in some nuclear plant. And so you have on one side of a shield, you have a very large flux of particles. Then you design a shield, a concrete shield with some thickness, and you want to estimate with the simulation what the flux of particles and what are the characteristic of this particle which are able to cross the entire shield. And so these a few particles which are able to cross the entire shield, which are indicated on the picture with the red arrows and with the green ellipse. These are called rare events. So these are not events in the Gen 4 terminology terms. It's events in the terminology of how the people working in biasing call them. So these very few particles are so-called rare events. And what happens in this case is that you see that you have this thick shield, which is meant to absorb the particles. So you have a large incident flux, which is generating a lot of interaction inside this thick shield. And so the shield does its job, that is, it absorbs all these particles, which means that you are spending a lot of computation time inside this shield to, at the end, have only very few particles going outside. And if you are interested in that, and you are interested in that for radio protection problems, then you have a very inefficient simulation. At the opposite, you have the case of the very thin detector that Alberto already mentioned. That is, assume you have a very thin silicon layer, which is meant to detect neutrons in the flux of neutrons. Then, because of its thinness, you will have only a very few cases in which you will have a neutrons interacting inside this small volume. So you will shoot plenty of neutrons in your simulation to only have a few which are interacting inside this thin layer. Or you may have also the case, which is for example, the case of what happened in space, of a very small volume. Let's say, for example, a CPU or an electronic device, which is the critical part, let's say, of a system, of a satellite. And so if you are doing the simulation of that straight away, you will send a lot of particles on the satellite structures. You will have a lot of interaction, but you will have only very few tracks which will cross the volume. And so again, your simulation will be very inefficient because the target, that is the small red volume, will have only very few particles going through, while this is the most critical part you are interested in. So the so-called analog simulation, that is the standard one, is very inefficient to address these problems. So next slide, please. So what is event biasing? So event biasing or variance reduction is a set of techniques which are meant to simulate real event efficiently. So this is an accelerated simulation with respect to this event and to this event only, that is not everywhere. And what it does in practice, I would say, is that if you start with an analog simulation, then what happens is that you will spend most of the time, most of the bulk of the simulation time, simulating things which are not in the critical part of your simulation of your application. And then what you try to do with the biasing is that you take off part of the time of the bulk of the simulation to put that between quotes on the real event simulation. And so doing that, you will enhance by large factor the time you spent on real event simulation. So this biasing can provide a very large CPU improvement, and this is typical order, several orders of magnitudes is something which is quite achievable. You can gain 10 to the 5, 10 to the 6, or even more, depending on the problem. And so biasing stands for bias simulation, and it is biased because rare events are enhanced compared to the analog simulation. So next slide. So main principles. So there are a large variety of techniques which, when you go through the literatures, have sometimes different names, but to tell about essentially the same things. But these techniques are essentially relying on two underneath classes of technique. So we have the important sampling, where in fact you modify the physics distributions to enhance the important part of them. So I assume, for example, that the green distribution is an energy spectrum, and that you realize in your simulation that the part which contributes the most to your simulation is the high energy part. But you see that you are sampling a lot of particles at low energy, and which are essentially a waste of time in your simulation. So the idea of the importance sampling is simply to replace the analog probability density function by a biased one, the blue one, where you enhance the interesting part of the problem. And then in this case, you will associate each time you sample X value, you will associate this X value with a weight Wx, which is the ratio of the two probability density function. The other class of techniques is the so-called splitting, which comes often with the killing. In this class of techniques, what you do is that you keep the probability density function unchanged, but you split when you move towards the region of interest. So on this little drawing, you have on the left the incoming particles, and on the right, you define a region of interest. So here I've shown something which looks geometrical, but in fact, it can be anything in the phase space. That is, it can be geometry, but it can be also a region of energy or an angular region or whatever, which is relevant to your problem. So what you do with the splitting is that you have an incident track, which at some point reach a boundary of the region, and then you split this track. That is, you are making n identical copies of the same track, and each of the copies then have a weight which is divided by n compared to the initial weight of the track. And you continue. And you let the simulation goes. Then what happens is that some of these copies will be absorbed inside the simulation, but some of them may be able to reach the next boundary. And then you restart the game. That is, you split again on this boundary, again divided by n the weight of the tracks, etc. Up to the point that you then reach the region of interest. What And then with this, the idea of the splitting is that with this artificial splitting, with this artificial enhancement, you are compensating for the natural physical absorption inside your problem. So you compensate with this splitting, the physical absorption inside your problem. This I mentioned that the splitting comes in general with a killing. That is, and this is for the case of particles which are going in the wrong direction. That is, if you have a particle which is receding, that is going from the region of interest, that is going away from the region of interest, then when it reaches, when such a particle reaches the boundary, you will apply a Russian roulette, and in this case, you will give in a probability of 1/n to survive. And so if it survive, if it dies, it dies. But if it survives, then you multiply its weight by n, and you continue the thing. So I mentioned that several times about the weight. So with the biasing, you enhance rare events in the simulation, and you keep track of these enhancements with these weights. And then what you do is that when you compute a physical quantity and assume, for example, that this small box we are computing the total energy deposit, then for each of the track which is crossing this volume, each of the track of this track has some weight Wi, and which each of them is depositing some energy, and then you simply weight the energy deposit to get the energy total energy deposit, and this total energy deposit with applying the weight will correspond to the one you will observe with a standard analog simulation. So next slide. So some example of impedance sampling technique. If you are familiar with MCNP, they have what they call the exponential transform technique, which is a change of cross-section which is made angle dependent. That is, it favors the penetration inside the shield when you are going forward. And it does that with putting a smaller cross-section forward and a stronger cross-section backward. So if I start from the analog law on the left one with a classical exponential distribution, then when you are moving forward, you will use a weaker cross-section so that you can penetrate deeper inside the shield. And if you are going backward, then you are using a stronger, let's say, absorption cross-section so that your particles will disappear quicker. At the opposite, there is the case of this thin volume and the force interaction that Alberto mentioned before. It means that if you have an analog law and with a small volume, it means that the small volume only intercepts a small fraction of the exponential distribution, meaning that then you have a low probability to interact inside this volume. So what you do is that you change this analog law with something else. So it can be an exponential law, but it can be in fact anything else. And you bound this distribution so that you are guaranteed that the integral of this distribution is 1 over the domain. So you are, in this case, forcing the interaction to happen inside this volume. So in terms of cross-section, if you speak in terms of cross-section, then you have a cross-section which is a kind of strange thing. That is, the more you come close to the end of the volume, the higher the cross-section is, and in fact, it diverges when you are very close to the end of the volume, which is guaranteeing that in fact the interaction will happen inside this volume. So next slide. Example of splitting. So I just show, in fact, a direct application of what I explained before, but in the geometrical case. So what you do is that you have a shield, which is made, let's say, for example, of concrete. And what you do is that you split this shield with slices that you have tuned in such a way that it is appropriately made so that your problem converges correctly. So you have a large incident flux on the left, and then each time a particle reaches a volume boundary, you split it here by a factor 2. And then again, you compensate this absorption inside the shield by this artificial splitting. And again, if it goes in the other direction, then you apply a killing procedure that is a Russian roulette, which is a 50% probability to survive for this drug to survive. Okay, we can go to the next slide. So biasing does not come for free. That is, it has some strengths, but also some difficulties. So the strength of the biasing is that the physics in the biasing is the same one than in the detailed simulation. You don't introduce approximation in the physics. And biasing, I would say, is simply another way to process the detailed physics. So it means in particular that when you need to explore tails of distribution which are far away from the mean value, you are guaranteed that what you do with biasing is the same, will be the same that what you will do with a full detailed simulation, but which will take an enormous amount of time to go there. So it means that the bias and analog simulation results are in fact statistically identical. The difficulties with biasing is that as mentioned, this is dedicated to rare events, so only rare event problems can be treated this way. And the main difficulty is to ensure a proper convergence, which sometimes can be difficult. The thing is that the drugs are given a weight, and these weights may sometimes have a large spread, and which can cause problems. And so the issue is that from time to time, you have a random appearance of weight, which are very large compared to the other weight you have scored up to now. And so this causes, if you are monitoring the convergence of some observable, some mean value of an observable, you may see something like it is shown on the graph on the right. That is, you are in this case calculating a mean value of some observable, which is in this case should converge to 0, and you see that you have this strange behavior of something which is from time to time rather smooth, but then you have these big drops, which are due in fact to large weights. And when you see that, in fact, you see that you have the feeling that you are almost going to converge, but then you see you have a big drop, which is telling you that you are not converge at all, and that it will take time. So the difficulty with biasing is that is to ensure that you are not missing, that you are properly converging on the correct value. So in the annex, I can show something about that. And the last point is that in most techniques, the correlation between observable is lost. So this is something which can be sometimes annoying. In most of the cases, you are interested in mean values, but if you are interested in correlation, then you have very few techniques which are preserving the correlation. So next slide. So let's go to the biasing option, which are existing since quite time. So you may have seen the general particle source tool during this week. And so this tool, this GPS, has various options to allow biasing. So assume again that you have so it provides position, angular distribution, and energy distribution biasing. That is, if some part of the energy distribution is more important than the other part, then you can enhance it with a bias distribution. And Geant4 will propagate the weight for you inside the simulation. So this is a classical importance sampling. Yes, okay, so we can go to next slide. Alberto already mentioned several options in the hadronic. So the cross-section biasing, where you can enhance the cross-section of some hadronic process when they have low cross-sections. But this is something which is not that easy to use. And in particular, there is no messenger. So it means that you really have to edit the physics list if you want to go for that. So the next slide. Albert also mentioned the leading particle biasing. So this is a way to treat the shield problem when you want to see what are the particles which are exiting the shield. So the way it works is that you have a particle which is entering a volume. Then at each interaction, so you have the various types of particles. You have the blue, the green, and the red. So the red is the leading one, so you keep it at each interaction. And then what you do is that you trim the other particles. So you keep one particle of each species randomly. So you keep the green one because this is the only one, but you keep one of the two blue one randomly. Then you continue, and at each interaction, you repeat this thing. That is, you keep the leading particle, and then you trim the other one, killing randomly particles which are the same species. And doing that, you see that you will simulate far less particles inside the shield, and you will get faster the answer of particles which are then exiting this shield. In the reductive decay module, there are several options which exist. That is, you have the ability to displace the simulation of the reductive decay inside a given time window. You can also modify the decay channels, the probability of the decay channels which are with which the particles are emitted. You can also split the parent nucleate, etc. So, okay. So next slide. And as an option, there is also the geometry-based importance biasing, which is a direct application of the splitting we mentioned before. So what you do is that you attach importance to cells in the geometry. That is, you artificially divide the geometry into cells, and you attach so-called importances inside each of these cells. And the weight is the ratio. The splitting factor is the ratio of two consecutive weights. So again, I would simply repeat that if you go from the slice with importance 8 to importance 16, then the splitting factor will be 2, and so you will split the track by a factor 2. So we can go to next slide. How can you use that? In your main program, you will define these importances, and for that you will use this importance store. And this importance store has this call add importance geometry cell, where you pass the importance value, and then you pass the physical pointer. And so you have seen that this week that you may have replica, which is in fact a single physical volume, but which is placed many times. And so if in case you have a replica, you can specify a weight to each of these slices, of these replica slices, specifying by the index of this replica number. So with that, you define the importances. Then you tell John for which particle you are applying this biasing. And so you do that with this G4 geometry sampler. So you tell that these things will be active from the word volume and for neutrons. So you see here we specify word volume, which means also that you can use this biasing for other geometries than the word volume, and you can apply that to parallel geometries. So I don't discuss that now, but here instead of word volume, you can use a parallel geometry. Then once you have, so these lines allow you to set up the configuration of the biasing. Then you need to do some technical trick so that Gen4 can handle that, and it handles that through technical processes, I would say. And what you do is that you start with a classical physicist, for example, FTFP-BERT, and you create memory a physics module, which is default importance biasing, in this case, passing the proper geometry sampler. And when you do that, in fact, you are augmenting FTFP-BERT with this new facility that will then handle the splitting and the killing on the surface boundaries. So we can go to next slide. So this is an illustration, and so I wanted to make a demo, but since I cannot share my screen, it's a bit of frustration. So it's just a picture of what looks like splitting with this geometry technique. So on the left, you have the analog simulation. That is, you have a block which is sliced, and you see, and so we shoot here a neutron. And so you can guess that it will be very difficult for neutrons to reach the other side of the shield. So when you apply the biasing, then you activate this artificial splitting on the boundaries, and you have this kind of strange shower, which is here shown. And you see that very easily you will have statistics going through the entire volume. And so you will be able to estimate the flux of neutrons which are crossing, in fact, this volume. So next slide. Wet window technique. So the wet window technique is a splitting and killing technique which has been invented by the MCNP people again. And this is to control, in fact, the range of weights which are going through your simulation. So the aim of the wet window is to avoid to have too high weights at some point. That is, when you have very high weights, as I shown before on the graph, you may have problems of convergence. So the idea of the wet window is that you have learned about your simulation, where are the typical weights you can expect. And so you set up wet window which are volume geometry dependent. If a particle has a too large weight compared to this wet window, then it will split, so that each of the copy will then fall inside the wet window you have defined. And if you have tracks which have too low weights, then these tracks are simply a waste of time, because of their low weight, they will not contribute much to the mean value. So what you do in this case is that you apply a Russian roulette with a probability such that if the track survives, then it goes inside the wet window limit. And this is a technique which has been invented by the MCNP people, and it helps really the convergence. So at the same time, it helps the convergence, preventing to have too large weights which are destroying the convergence, and it also saves time by killing these too low weight tracks. So next slide. And then you have a class which is user-defined biasing, which is a wrapper class which allows you to, in fact, modify the final state generation. And for that, I can give the example on the next slide, please. So this is applied to the so-called Bremsstrahlung splitting, which is a technique, for example, used in medical application. The thing is that when you have a Bremsstrahlung, the way the people in medical make this gamma production is that they send an electron beam on some thin target, and then you will create some Bremsstrahlung. But in the simulation, the thing is that the probability to have the Bremsstrahlung may be rather low. And each time you have a Bremsstrahlung, you have at most one gamma. And so again, your simulation will be very slow, because you will need to send a lot of electrons through this foil, to have enough Bremsstrahlung photons. So what does the Bremsstrahlung splitting is that you repeat, in fact, the sampling of the final state when you have a Bremsstrahlung, and instead of shooting one Bremsstrahlung gamma, you shoot, let's say, 100 of them in one interaction, giving each of them a weight which is 1/100. So you do that with this thing. So there are a few lines of code here. The important thing is so the important thing is that so you have the lines which G for int e equals 0, e smaller than fn split. So fn split, sorry, is the number by which you will split the incoming particles. So you see that you are in fact with this particle change blah 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 post step do it, you are in fact calling n times the final state generation. And what you do is that you store in this secondaries vector that with this pushback, you will store each of the Bremsstrahlung gamma so that you fill this vector with this same sample state, which is a final state, which is sampled many times to generate hundreds collisions at one time. So an expression of that is shown on the next slide. So on the left, you have the simulation with no Bremsstrahlung splitting applied. And with and on the right, you have the same simulation, but with a splitting factor 100, meaning that when you have a Bremsstrahlung, you instead of having only one Bremsstrahlung interaction, you sample 100 times the final state, so that you have 100 gammas which are emitted. And so with that, you have much more a simulation which is much more efficient. So next slide. Reverse Monte Carlo. So next slide, thank you. So this is a fancy simulation in which the particles go back in time. So the use case is shown on the right. So you assume you have a device, and so typically this is a satellite in which you have a small critical part, which is the red one, and which is typically, let's say, a CPU. The silicon of a CPU, which is there to control the satellite. And this small volume may be of the order of a few millimeter cube, while this thing is placed inside a satellite, which is of the order of the Mach cube volume. So you see that just by comparing these two things, typically you will spend a fraction of time, which is the fraction of volume. So it means that you will spend a fraction of time, which is the 1/1 billion inside the target, while this is the critical part. So next slide. So if you do a straight simulation, so you will have particles which will be generated from the sky. They will do many interactions inside the big structure, but you see you will have then a very low probability that one of them hit the small volume, and so you'll have a very poor estimation of the dose inside your critical part. So next slide. So what you do with the reverse Monte Carlo, you start by defining a region of interest, which is surrounding the target volume. And then you have adjoint processes and adjoint track. That is, you start from an adjoint track on the region of interest. And this adjoint electron, in this case, we do reverse processes. And so with a reverse compton, it may become an adjoint gamma, which may become, again, an electron by a reverse Bremsstrahlung, etc. So it will do backward simulation this way, up to the point it escapes the structure and reaches the sky source. And then, next slide. So if you start from some spectrum on the region of interest, and so you have many tracks that you then propagate back in time. So you start from a spectrum for the regions of interest. Propagating all these particles back to the sky will make you a spectrum on the sky. Then you know the actual spectrum on the sky, and then you just need to normalize by just a ratio of the two spectra, so that you get the weight of each track which has been generated backward. So once you have propagated back all this track back in time, you estimate their weight. You are able to estimate their weight, and then in the second phase, you take all these particles and you propagate them forward with the standard simulation, and take into account the weight you have estimated on the previous stage. And so doing that, you see that you will gain very large factors, because you will typically gain the factor which is the ratio of the two volumes. So next slide. So this is an example of a convergence speed using the reverse Monte Carlo. On top, you have a model of satellite. In red, these are parts that are critical in this simulation. And so on the graph below, you see a convergence speed. So we are measuring, we are calculating the dose in some volume on this graph. So you see that with the reverse Monte Carlo in red, you quickly converge to some value and in a few hundreds of minutes. While you see that for the analog simulation, so the standard one, even with 100 times more simulation, you are still far away from a convergence, and so you still don't know what is the dose you have in these red parts. So next slide. Okay. Next one. Okay. So what we have seen up to now is that we had in John 4 various options, but the thing is that often in a problem you may want to combine them, and it was not easy to combine them because they were designed, I would say, separately. So the idea of the generic biasing scheme is to have a general scheme that should accommodate all these forward biasing techniques. So as a general object-oriented thing, you define an abstract layer, and then it provides some options ready to go based on this layer. And given this is an abstract layer which is open to users, you may implement your own customized options if you don't find in John 4 the ones you are interested in. So this scheme handles two types of biasing. So it handles, in fact, the impedance sampling and the splitting techniques. So the impedance sampling is handled with the so-called physics process biasing that we denote as physics biasing. The splitting killing are denoted as non-physics biasing. And so the aim of this scheme is to be modular by defining in some way some primitive of biasing that then you can combine to provide a biasing scheme. So let me illustrate that on the next slide. So this slide shows what is the force collection scheme as defined in MCNP. So in this scheme, you have a thin volume, and what you do is that you have to account for, so you want to account for two things. You want to account for particles which interact inside this thin volume, but with a very low probability, and you want to account for the other part of the flux, which does not interact inside the volume. So the force collection scheme of CNP does the following. That is, you have an incoming particle with some weight, then you split it on the boundary of the volume. Then for one copy, you force it to go through the volume without interaction, and so it goes out with some weight. And for the other copy, you force it to have an interaction inside the volume, and this happens also with some weight. The thing is that you see that we have a kind of atomic components. That is one thing which is the cloning, another one which is the force non-collision, and there's one which is the force collision. And so the idea is that to consider that as biasing primitive, that we call biasing operation, and then we combine them to provide the biasing scheme. So these biasing operations are this splitting, force interaction, and then these things are combined in a so-called biasing operator, which then handles whatever operations it may want to implement a biasing scheme. So next slide. So this is to give a bit more details about this scheme. That is, the basic thing are this biasing operation in red. So this is an abstract class. These things can handle physics process. That is, you can pass a physics process to a biasing operation. And then this biasing operation will act by providing the possibility to modify the interaction law and modify the final state generation. And if no physics process is passed to this biasing operation, then it does simply splitting or killing. Then this series of operations that you would select, in fact, are handled inside a dedicated class, which is the biasing operator, which is called, in fact, at the beginning of the step, to give you the opportunity to change whatever, to make whatever decision on this step, that is either doing nothing or changing the interaction law or decide to split at some distance. And then it is called also at the end of the step to again give you the ability to do whatever you want at the end of the step. That is maybe change the behavior of the physics process. That you may change an interaction, an angular distribution by something else, etc. So this is to set up the biasing, and then to have that working inside Jan 4, we have this biasing process interface, which will talk to these classes and make the interface with the tracking. So what we do is that this biasing process interface, you can give it a process. In this case, it encapsulates the process, and it controls the process. So this is when you want to change the interaction law of this process or modify its final state interaction. Or if this biasing process interface is not given any process, then it will simply handle splitting and killing, which are, I would say, process independent. Then a cartoon on the next slide. So this is the usual classical way, that is assume you are tracking a gamma. Then you limit that to photoelectric, gamma conversion, and quantum scattering. So you know that in the first step, in the first stage, you call the get post-physical interaction length. Each of these process return a length that is the length at which it will act. And in the second stage, then the gamma is moved, and then when it reaches the end of the step, you call the post-step duet of the process which answered the smallest length. So this is the usual scheme. And then next slide. When we go with the biasing, so all these processes in this case are encapsulated, and so still on the first stage, on the get physical interaction length, the interaction lengths are sampled, but then this is made through this biasing process interface, which may then use a biasing operation to decide to modify the interaction law. And in the second stage, that is at the end of the step, when the post-step duet is called, the biasing process interface may also change the process behavior depending on the way on the biasing operation it may receive to modify the final state generation. Next slide. And if you put in addition a biasing process interface with no process, then you give the ability to the biasing scheme to also perform splitting and killing in competition with the other processes. So next slide. The way it works is that we associate this so-called biasing operator with a volume. So this is a cartoon on how it works. So on the left, we have processes which are encapsulated and something which is a biasing process interface with no process, which is then here to do splitting and killing. So next slide. So as long as the track is traveling inside the volume with no biasing, then all the calls of the tracking that the interface is receiving are sent back to the underneath physical process. Next slide. And next slide. And when we reach the volume where there is biasing, then the process sees that there is a biasing operator which is associated to this volume. And then all these interfaces are then asking this biasing operator what to do. So next slide. So the operator in this case says do a splitting. So the guy with no process will do the splitting. Next slide. Then we start continue with the tracking of one of the copy. Next slide. And so the biasing process interface then asked the biasing operator what to do, and it said do a force interaction inside the volume. And next slide. So the tracking continues, and at some point, next slide, we come to the second copy, and again, this thing is asked the operator what to do. Next slide. And it says, please do force a free flight through the volume without interaction. And with that, in fact, we are re-implementing the MCNP biasing scheme. Next slide. So how to use? It's pretty similar to what we have seen before with in fact, many times. We assume you start with a FTF fibert, a physics list. And then you define this physics operator, GFR generic biasing physics, which holds, in fact, the machinery of processes doing what was explained before. And you said to this that you will bias a gamma and neutron. And so by doing this call, in fact, in the backscene, Jump4 will encapsulate the physics processes and do whatever so that all what I explained before will actually take place. And then with the physics list register physics, you are equipping the FTF pibert, you are extending the FTF pibert with this new functionality so that Jump4 can handle that. So there are many more nuclear gisting. I don't comment on them. And then inside your geometry, in the construct SDN field, you create your biasing operator, which you have selected, and you set this operator that it will be active in some logical volume to bias. So next slide. So there are a set of functionality which are provided as examples. The first one, GB01, is, as Alberto mentioned, is shows a way to bias a cross-section. The second one shows how to use the force interaction scheme as implemented that is imitating the one of EMCNP. The third one is re-implementing, in fact, the geometry importance sampling that was existing before, but it is re-implemented with the generic biasing. And given then we are writing C++ code, it's easy to add more options to that, to have in some way a non-integer splitting. That is, we give the ability to have a probability to do the splitting. That is, it may happen that a factor 2 is too small and the factor 3 is too high. That is, with 2, you don't split enough to reach the other side of the volume. And with 3, you diverge. So you are shooting too many, you are splitting too much, and you have too much particles inside your simulation. And so with these things, you have a way to adjust with a probability to do the splitting. So in this way, it is equivalent to have a non-integer splitting value. GB04 is a reimplementation of the Bremson splitting. GB05 is a splitting by cross-section. So this is a two minor edge in invention. That is, if we speak about the splitting, if we speak about the exponential transform, you see that no, sorry. If we speak about the splitting, you have to adjust the slices thicknesses to the problem. And in fact, what you do is that you adapt the thickness of the slices so that you compensate the physical absorption with this artificial splitting. And you have to tune this slice thicknesses so that it doesn't happen too often, or it happens often enough, but not too often. And the idea of this splitting by cross-section is that the biasing collects, in fact, all the absorption cross-sections, and it splits forward using the absorption cross-section so that it compensates exactly the absorption through the splitting. And so you don't need to define slices anymore. You just rely on the physics, and you compensate exactly with this splitting. You at the same rate that this is physically absorbed inside the shield. With GB06, this is the geometry imbalance splitting, which is applied but with a parallel geometry. So I don't know if you spoke too much about parallel geometries, but in this case, assume you have a very complicated geometry in your tracking geometry. That is, assume you have a satellite or whatever, and you want to do splitting. And if you have to insert slices inside the complicated geometry, this is very complicated. So the aim of the parallel geometry is that you define a geometry which has the same dimension that your tracking geometry, and inside this geometry you define a volume which overlaps with your tracking geometry and which define the slices. So whatever complication you have in your tracking geometry is not seen in the parallel geometry, and so you can easily define slices which are physically not existing inside your tracking geometry, but which allows you, in fact, to split where you need without having to completely re-edit your geometry in a complicated way. And the last scheme is, in the last example, is a reimplementation of the particle leading scheme. The next slide. So in summary, biasing techniques can provide very large acceleration factors in problems in which what you need to tally are rare events. So the answer proposes many biasing options. There is this generalized approach, object-oriented since release 10, which is aimed to I would say factorize all the possible forward splitting. So the thing is that these techniques are delicate to handle because of the possible issues with convergence. But in some problems, they are simply unmissable because in some problems, you simply have no way than using biasing because an analog simulation would take forever. Thank you.
Thank you, Marc. There are a couple of questions which are from the room, but they're anonymous, so maybe I'll read them out.
Yes, thank you. So regarding the thickness of artificial the splitting slice in the page 9, do you have any recommendations for the starting point? For instance, it should be x times of mean free path or the cut limits of a specific particle?
Yes, it should be typically around the mean-free path. Yes. Yeah.
Okay.
Yeah.
And my second question is in primary particle biasing, if I am implementing angular distribution biasing using GPS, do I need to calculate the weight manually, or can I get it from like G4 class?
So if you provide, so if inside the GPS you have the analog angular distribution, and if you provide a biased angular distribution, then the GPS will calculate the weight for you.
Okay, thank you.
So my question regarding cross-section biasing with the general biasing scheme, that what is the best way to avoid the over biasing? What are your recommendations regarding that?
So you may give a bit more. I would say my recommendation is to try. If you have a problem, so you need to learn. You have a learning phase when you are doing biasing. You have a learning phase where you have to start with to make a gross estimate of the thing, and so when you over split, then you see that your application simply does not come to the end, and so you know that you are over splitting. So yeah, you have to do several attempts to start to have a reasonable understanding of the level of forcing you have to use. Yeah.
Okay, and I have a couple of other questions as well, if I can. And you mentioned that so not all biasing techniques can reserve correlations between observables. And what are the techniques which can be used in such case to reserve correlations?
So to my knowledge, there is the so-called IMS that is something that may come that we plan to have in Gen 4. This is when you start from a source and you have a target which is far from the source, and you have a complicated path to reach the source. And what they do, in fact, they start to they have a smart technique to start to calculate a map of importances that will help to, I would say, to drive the flux toward the source. And when you use this technique, in fact, you preserve the correlation. That is, you preserve the correlation with this technique. But there are not so many. I try to remember others, but at least this one is preserving the correlations.
Okay. But we don't have one in Gen 4 that undertakes this.
Yeah, for now we don't have. Yes. Yeah.
Okay, and you showed that with generic biasing, it's pretty easy to add or define this generic biasing for particles like neutron or gamma. But what about the generic ions? I've tried it. It's not that straightforward. How is it possible to use generic biasing for generic ions?
So it's part of the work plan since I have to confess several years to extend that to charged particles, and this is something I hope that will come soon. The problem is that with charged particles you have because of the ionization you lose energy, and so the cross section are changing. And when you are doing the sweat calculation, in particular, so you have along the path, you have to compute what we call a non-interaction weight, and this one involves the integration of the cross-section along the path. This is easy for charged particles because their energy doesn't change along the path, so it's just a multiplication.
Neutral.
So it's easy for neutral particles, yet neutrons, yes, because they are the integral is simply the cross section times the step length. But for charged particles, you have to integrate, and if you do that, then it's very complicated. We have a technique which is I would say validated on toy Monte Carlo, which which avoid to do that, and which is inspired by, in fact, the woodcut tracking, and inspired by the same technique which is used in the electromagnetic physics, where they have a change of cross-section along the path. So this is something I hope we will provide, but for now this is still not provided. So the point is really that is with charged particles you have to take into account the change of cross-section along the path to have that correctly. And so it's not straightforward. Yeah.
Okay, and my last question is about reverse Monte Carlo. That if I know correctly, it's rather for electromagnetic physics and particles. But
Yeah.
can one use for hadrons such reverse Monte Carlo, or is it planned for the future?
So this is only for electromagnetic particles for now. Yes. Yeah. And I'm not sure this is planned to be extended to hadronic particles.
Not to my knowledge.
Yeah.
No, I'm not aware that is in the plan of Laurent to extend it to hadronic physics.
Yeah. You have a specific use case in the.
No, I'm just curious.
Okay.
If it's planned, but yeah, thank you very much.
Just for a parenthesis, the amount of effort to implement reverse physics processes is very significant. One needs to look at and understand in depth and invert. So it's not a simple process, but for hadronic physics, probably be even more complicated because of the number of potential. When you have an interaction, you have a lot of things coming out of it. So it's not as obvious how one would undertake it. I would expect.
Yeah. Do you want me to say a few words about convergence problems?
If you want to add something.
Please. Yes.
Okay.
Do we want to go back to some slide or do you?
At the end of the presentation, yes. Yes. So yes, again.
Backwards.
Yes, backward. Yes. Okay. Here. So yes. So next slide. And we can go again to the next one. So just to illustrate, in fact, the issue with the convergence. So assume that so when you are doing biasing, in fact, you are trying to estimate typically a mean value or something of a distribution you don't know. So assume that this distribution we don't know is the yellow one. And so when you are doing biasing, you will try to sample this distribution with another distribution, so next slide, which is the blue one in this case. So I deliberately chose a very bad sampling, that is, we don't know where is this yellow, and we try with the blue one to find where to reconstruct it, in fact. So you see that in this case, we have a very bad sampling because this yellow distribution is a sigma of 1, and it's centered on 0. And the blue one is also a sigma of 1, as is centered on 3. So it means that all the negative part of the yellow distribution is more than 3 sigmas away from the mean value of the blue one. So which is an ill-formed problem. But let's see how it goes. So we sample, that is, we shoot random numbers using the blue one, and we calculate the weight so we know how to calculate the weight. So next slide. So what you see is that when we sample 100,000 events, so we do 100,000 random number generation with the blue one, and for each of the value we calculate the weight. And the yellow part is the way we reconstruct, in fact, the yellow Gaussian. So this is you see that you don't recognize it essentially, And if you try to estimate the mean value of this quotient, which we know this is 0, then we have this curve below, where in fact we accumulate the data to compute the mean value. And you see that you have this curve where you look to have some smooth spot, and from time to time you have a big break going downward, and which in fact is a signature of the problem. So next slide. So what you see in such if you would plot the weights, you will have this distribution. That is, you have here a very pathological case where you see that you have lots of tiny weights. That is, you have yes, lots of tiny weights, and you have a few ones which are very large. That is 10 to the 2, 10 to the 3. And so what happens is when you see a big drop inside the mean value convergence, in fact, it is when you get a very large weight, which is dramatically changing the convergence, the mean value convergence, and which causes this big drop. And in fact, if we, yes, let's go back one slide. And so this large weight, in fact, are due when, so you see that with the blue one, we are essentially sampling the positive part of the yellow distribution, and we are not sampling enough the negative part of the yellow distribution. And so from time to time, when you are 3, 4, 5, 6 sigmas away from the mean value with the blue distribution, that is with very low probability, you are still in a very comfortable range for the negative part of the distribution. That is, if you want to get a value which is -2 for the yellow distribution, you are simply 2 sigma away from the mean value, but you are 5 sigmas away from the blue one. So it means that with the blue one, you sample very rarely this region. And when you hit this region, this is where you come with very large weight, and these large weights are telling you you are not sampling this part enough, and this is why they come with very large values. So next slide and next slide. But mathematically, this is not wrong. That is, if we shoot more values, and instead, if we sample with 10 millions of value, then you see that, yes, you start to reconstruct something which looks like a Gaussian with the yellow one. And then you see that, yes, you are converging properly at the end to the proper mean value. So, and next slide. When you are doing fact biasing, these are the set of criteria like this that you have to keep in mind. So there are several things that are signs of alerts in this sampling problem, in this ill-formed sampling problem. So you see that we have a wide variety of weights. We have many tiny ones, which are in fact simply waste of time to determine the mean value. And we have few huge ones, which are responsible for this jump in the mean value convergence. So these signs that you are not properly sampling the problem, that you are not properly sampling the problem. You are missing. There is part of the problem that you are not sampling enough, and which are causing, in fact, these large weights to come. Then this is where you could, for example, use a weight window technique. So in this case, it's not possible because it's too simple problem. But then using a weight window technique will allow you to alleviate partly this problem. And the thing also with this very huge weight that we have from time to time, you have to be you have to consider that they are not wrong. That is, the temptation from time to time would be to say, oh, they are just a few pathological values, I drop them. But in fact, they are not wrong by themselves. You see that if you let the problem go, then you see that you are converging correctly, and that this very large weight are simply driving back the mean value to the correct value. So the thing is that you should not dismiss this large weight, but you should consider them as an alert that there is part of the problem that you are not sampling enough. So take that as an alert that something is not properly sampled in your problem. And we also this sort of monotonic increase of the mean value. And this is due to the fact that with the blue distribution, we are sampling essentially the positive part of the distribution. So we have this kind of monotonic increase of the mean value, which is also an alert to be considered. And that is when you have a mean values which looks to have a kind of systematical drift like this. This is also an alert that you are missing part of the problem. So there are several convergence criteria like that, and they have been in particular established by the MCNP people. And there is a class in Gen 4 that calculate, in fact, all these various criteria, and that you can use to, in fact, be confident that you are not missing part of the problem, that your convergence you obtain with the biasing is correct. Questions?
Thank you, Marc. I don't see any questions. I didn't see any question on Matamos. So I think that we have provided what people were hoping to get, or we have exhausted people.
Maybe.
Possibly both. The idea was to have the chance to actually ask questions about other topics. So let me